Hello and welcome to Statistics. This is Unit 5 and this is Miss Gallus a good free throw shooter? In today's lesson we are going to be discussing the long run probability, law of large numbers, and simulation. Okay, so what we did in class is we went to this app. If you want to go ahead and simulate it yourself, you can. And we went ahead and simulated what Miss Gallus's free throw percentage would be. So it has already a predetermined free throw percentage. So every single time that it's shooting, it's going to make it or miss it determined on what the free throw percentage was that we programmed in. So when we did it in class, this is what we got. And we recorded how many makes we got out of the shots, and then we did the percentage. In ours, it looked like 80% was a pretty good guess of the free throw percentage because it kind of kept honing down towards that number. Notice it kind of kept going over and under and kept, and it seemed to level out around 80. If we noticed as the more throws we made, the more accurate it was, because you can see it started at 100% and then dropped down 33% less at 67%, and then jumped up and then jumped up. And then anyway, then started to settle towards 80% as we started to have more and more throws. That's called the law of large numbers. What the law of large numbers does is as my sample size increases, the actual probability gets closer and closer, or the sample probability, gets closer and closer to the actual probability. On number 4, it says we are interpreting what an 80% probability is of making the free throw. And basically that means Miss Gallus has an 80% chance of making each free throw. And then remember, if you take a very large sample, then what happens with Miss Gallus is about 80% of them will be made. For number 5, it's you're going to go ahead and click it until you get 53 throws, and you're going to see that in our simulation we got 82%. Every single simulation is slightly different because it's just a sample. It's not the true population, and it's not a true probability. It's just the theoretical, it's not the theoretical probability. It's just the actual working probability, which is going to be really close to 80%, but not necessarily exactly. And that's the answer to number 6 because of sampling variability. And then this one says, here are free throw percentages from all 30 students in class. And it says, what's the probability, number 7 says, what does 70% mean? And what 70% means, I've got it circled here, is one simulation of free throws in which Miss Gallus made 70% of free throws. And number 8, that's where the red line has to do with it, because number 8 asks you, use the results to examine the probability that Miss Gallus gets 70% or less if she's an 80% free throw shooter. And she has a 2 out of 30 chance, or a 6.7% chance of getting 2 or less, because you can see where there's 2 dots left of the 70% mark. All right, so the 3 things that the concepts that we went over today was, first of all, probability. Probability is a long run relative frequency. In the short run, it's unpredictable. In the long run, it's predictable. That's why in the short run, when you saw Miss Gallus was an 80% free throw shooter, but you saw the first couple shots really did not represent what her actual probability was. And then as we went further and further, you saw it got closer and closer to 80%. The second concept that we talked about was the law of large numbers. And the law of large numbers, if we do something many, 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 many times, the proportion of the desired outcomes will definitely approach its probability. And finally, a simulation. The simulation imitates a chance process, and that's exactly what we did when we did our estimation, is that we used a basketball simulator. I didn't go down to the gym and make the shots. I actually just used a simulator, and I plugged in that I want you to simulate what it would look like in an 80% free throw shooter. So it would give me a simulation of what potentially I would do as far as making or missing if I truly had an 80% probability of making it. And it's used to estimate the probability. Okay, let's look at the application of will the train arrive on time. So we're supposed to talk about this train that has a 90% probability of arriving on time, and it wants to know what the 0.9 means. And what it means is if you take a very large random sample of the 8 o'clock Princeton train to New York, that specific train at that specific time, please use the word about, because we're just saying this is the theoretical probability, but that doesn't mean that it might be a little bit more, a little bit less than 90%, but about 90% of them will be on time. Secondly, it arrived 5 days in a row. What's the probability it will arrive on time tomorrow? Same probability of 90%. It doesn't matter what happened in the past because they're independent one day to the next. One day does not affect the other day. And then number 3, it shows that it's giving me a scenario, and then it says, hey, how would I describe this in a 10-sided dice? Well, we're using the 90% probability of being on time. So we could have like 1 to 9, sides 1 to 9 be on time, and side 10 be late. You're going to roll it 20 times, taking 20 train rides. Each roll record whether 10 is facing up or not. And the number, if 10 is up, then that's late. And if 1 through 9 is up, then that's on time. So then you're going to record the number of times that I am late, per se, on number 10, or you're rolling number 10. So this dot plot that you're given, it represents 100 simulations, and you can see on number 4, first of all, it says what does 7 represent, and that's the simulation for which the train was late 7 out of 20 days. For number 5, you can see I circled all of this. Is basically I just counted all the dots. I got 17 on the first column at 3, 6 on the next column, and then 6 on the 5 column, and of course 1 on the 7 column. I added all those up and I got 30. And there's 100 dots, so that's a 30% probability that the train will be late on those 3 or more days. And then the actual results, we can see that yes, we're gonna say that, based on the results of 3 or more, we're going to compare it to the 5%. But since this here of the 30% is greater than 5%, then we're going to say no, it's not convincing evidence, because 30% happens really often. So we're saying, hey, is this unusual? And we're saying no, it's not unusual, because because that's what the claim is. And I didn't read to you that, but if you want to go ahead and claim this is what it's saying. And the claim is that 3 or more days, that it's very unusual for that to happen. And we're saying, no, not really, because when we looked at it, it happens 30% of the time. In statistics, if something happens less than 5% of the time, we consider it statistically significant. Okay, I hope that helped, and I will see you all later.